This detailed video lesson starts with a brief summary of how generators work, followed by an explanation as to what is meant by renewable and non-renewable energy. There is then an explanation of the factors that have to be considered when assessing the advantages and disadvantages of any energy resource. Finally, and for the bulk of the video, there is a detailed analysis of each resource, starting with non-renewables. Although very much larger and rather more complex than this, commercial generators operate upon the same principle, that is, of a coil revolving within a magnetic field. As the coil turns, the edges of the coil cut through the magnetic field, generating a potential difference, which results in an alternating current being delivered from the coil. The current is passed to the external circuit via sliding contacts, via brushes that slide against these contacts. Every generator needs an energy resource to make it turn, and in this case it's me. But commercial generators require something rather more substantial. Around the world, that energy resource is generally a fossil fuel. Gas and coal are the most common, but there is increasing use of renewables. First of all, we'll define what we mean by a renewable source and by a non-renewable source of energy. Renewable energy is considered to be an energy resource that is continuously being replaced. These resources include such things as solar, wind, wave, hydroelectric, tidal energy, and geothermal energy. Biomass, that is the things we grow and we can burn, is considered to be renewable providing it is replaced within a short period of time, which in most cases it can be. Non-renewable resources make up the majority of our energy generation at the moment. These include coal, oil and gas and nuclear energy. The problem with these is that the Earth has a limited amount of each, and it's quite likely that some, or perhaps even all of them, will run out within the next century. Politicians, and indeed science students, have to consider the advantages and disadvantages, the relative merits of each type of energy resource, and balance these against cost. And for every country, it is prudent to have more than one energy resource. If one fails, then you have others to fall back on. The things you may wish to consider are shown here. The cost of setting up a power plant varies considerably depending on the resource. For example, a gas station is fairly cheap to set up, whereas nuclear or hydroelectric are very expensive. The cost of the resource itself cannot always be determined. For example, the cost of gas varies a lot, whereas the cost of wind or hydroelectric, the resource, costs nothing. Some resources, such as wind and solar, are not reliable. You don't know if the wind's going to blow or the sun's going to shine. Some resources, such as gas and oil, come from countries which are not always stable, and where they have a world market, and the price might suddenly escalate. Some power stations, once they're built, will last for a very long time. For example, a hydroelectric plant might last as much as 100 years, whereas others, such as a nuclear power station, are likely to have a much shorter life. The environmental effects of power production vary widely depending upon where the plant is placed. Burning fuels produce CO2 and perhaps other noxious gases. A nuclear power station produces radioactive waste which has to be disposed of. Hydroelectric installations may flood large areas of land. Wind generators may be noisy and may be rather unsightly. There is a lot to consider. The safety of a resource has to be considered in terms of obtaining it. Mining coal, for example, is a dangerous occupation. And in using it, there are unlikely, but nevertheless could be catastrophic consequences to misusing nuclear power. Some power plants can be turned up and down very easily as demand varies. This includes all of the fuel-burning power stations and nuclear power and hydroelectric. Wind and solar energy, however, are not flexible. Coal is the energy resource used by a very high proportion of the world's electricity generation. They require a good rail link to deliver the large amount of coal required, and usually a nearby river to provide cooling water. These power stations often stand out because they are large, and they're slightly controversial because they produce acid gases, which causes acid rain, and some smoke and ash, although these amounts have reduced considerably over the last few years. The way that electricity is produced goes like this. Coal is fed into a boiler, usually as dust. It is blown in and burnt in the boiler to heat water. That water is heated to a very high temperature, well beyond its normal boiling point, because it is held under a very high pressure. Because of this very high pressure, steam can escape from the boiler at very high speeds, many hundreds of kilometers per hour. That steam blasts against a turbine. A turbine is rather like a compact windmill. So as it blows against the turbine, it makes the blades of the turbine spin very quickly. The turbine is in turn connected to a generator, working on the same ideas as the model we showed earlier. That spinning generator produces electricity. We use coal as an energy resource because it has many advantages. It burns easily. It's widely available, particularly within the UK. There are large reserves here and worldwide. It is fairly cheap. It is reasonably easy to transport and to store, and the power stations aren't complex. They're not too difficult to build, and they can be turned up and down easily depending upon demand. However, there are a number of disadvantages. It is non-renewable and will eventually run out. Coal mining is a dangerous occupation. People are hurt in coal mining every year. Coal is mostly carbon, so burning it produces a large amount of carbon dioxide. The impurities in coal, in particular sulfur, produces sulfur dioxide, which causes acid rain. And the mining of coal damages the environment surrounding the mine. After coal, gas is the world's second most common fuel resource, extracted by either direct drilling or by fracking. In this shot, there are two power stations next to one another, coal and, next to it here, gas. You can see that the gas station is very much smaller and produces much less in the way of smoke and fumes. The production of electricity from a gas-fired power station is in two stages, though it is unlikely that your syllabus will demand that you know the details of this. To begin with, the gas is burnt in a gas turbine, and the fast-expanding burning gases drive turbine blades, which spin to drive a generator, which in its turn produces electricity. It is a two-stage process because the still very hot gases from the turbine are then taken to a boiler where they heat water, produce steam, and that steam is used to drive a generator as it did in the coal-fired power station. Gas is widely used because of its efficiency and flexibility. When it burns, water vapour is produced, although some carbon dioxide is produced as well. It is very easy to transport. Gas power stations are relatively quickly and cheaply constructed. It is a concentrated source of energy. A small amount of gas produces a fairly large amount of heat. At present, there is a good supply of gas throughout the world. However, that won't always be the case. It is a non-renewable resource, and eventually the world will run out of it. In addition to that, a lot of the world's supply comes from politically unstable countries, and therefore the supply is not necessarily stable and safe. The world price varies beyond our control, and it is difficult to store large amounts in case there are problems. And finally, although it doesn't produce very much carbon dioxide, it does produce some, and therefore contributes towards global warming. Biomass fuels contribute a small amount to the British power production. One fuel that is grown in Britain is willow. It is cut, dried, chopped up, and then eventually taken to a power station to burn. Other examples of biomass fuel include seed, which is grown for oil, which is either burnt or used in the manufacture of diesel, sugar grown to produce alcohol, and again that is for use in the vehicles. Some plants and animal waste are composted to produce gas. As with every resource, there are advantages and disadvantages. Biomass can be cheap to produce, and it is a relatively available source of energy. If it's replaced regularly, then it is a long-term sustainable energy source, and if grown locally, it is reliable and secure. When it is burnt, however, it does produce atmospheric pollutants such as carbon dioxide, and it can only be regarded as renewable if the crops are replanted. Perhaps the major problem is that using the land to grow fuel reduces the amount available to grow food for the world's growing population. One of the examination questions you are sometimes asked is to explain the energy changes that take place when a fuel burns, when a power station produces electricity. No matter what the fuel, the energy changes are likely to be the same. Chemical energy is used, that is the fuel that is burnt. It produces heat and in turn produces potential energy as a store of high-pressure steam in the boiler. That fast-moving steam has kinetic energy, which spins the turbine blades, which also have kinetic energy. They drive the generator, which in turn converts the kinetic energy to electrical energy. The production of electricity from nuclear resources is mired in controversy and political argument. These arguments normally are around the safety of the installation. Nevertheless, at present, about 20% of British electricity comes from nuclear power stations, and there are plans to build more to replace these as they age. A nuclear power station uses fuel, but this fuel is not burnt. It is either uranium or plutonium, and it undergoes a nuclear reaction. The most commonly used of these fuels is uranium-235, and the atoms within it are split by neutrons. This splitting of the atom produces a large amount of energy and produces further neutrons which go on to split other atoms in a chain reaction. The neutrons produced are moving very quickly, and to split the atoms effectively they have to be moving slowly. This effect is achieved by using a moderator, usually carbon, which slows down the neutrons through collision. To slow down the reaction, control rods can be lowered into the reactor. These absorb neutrons. To allow the reaction to speed up, the control rods are raised. To remove the heat from the reactor, a fluid is circulated through it. This fluid is usually water. In an effort to ensure that no radioactivity escapes from the reactor, that water is used in turn to heat other water. The water in the heat exchanger becomes very hot, much hotter than the normal boiling point of water. It is under high pressure, and the steam produced is then used to drive a turbine, and the process of the turbine driving the generator is as before. The advantages of a nuclear power station are that when used properly it causes no atmospheric emissions. It is a flexible and reliable source of energy. The fuel can, to some extent, be recycled. Once the power station is set up, although it is expensive to set up, the cost of power production is low. And because a small amount of fuel produces a very large amount of energy, the fuel is easy to transport. As with every other resource, there are drawbacks. There is a small but very important chance of a high-risk disaster due to accident, earthquake, or tidal wave. The waste that is produced from the power plant is highly radioactive and will remain so for a very long time, thousands of years, and that material has to be stored. Leaks in the system can cause contamination, radioactive contamination of the environment. The power station is expensive to build in the first place, and the lifetime of the power station is limited, and it is then expensive to demolish. There are very few areas in the world where geothermal energy can be successfully exploited. New Zealand and Iceland are notable exceptions, having areas where the Earth's crust is thin and hot rocks are close to the surface. Shafts are then drilled down into this hot rock. and the rocks between them are cracked. Cold water can then be pumped down from one shaft to the other through the hot rocks, where it reaches a very high temperature and pressure. Under this very high pressure, the steam escapes at high velocity. It then drives a turbine, and the turbine in turn drives a generator. The electricity generated is stepped up to a high voltage for transmission to the national grid. The exploitation of this energy has several major advantages. It is totally renewable. The potential energy supply is huge, and it is used very successfully, as I mentioned before, in countries such as New Zealand and Iceland, where the Earth's crust is thin. However, in most places in the world, it is not practical. Where it is practical, it is still fairly expensive to set up. And as the water is pushed through underground, it is possible that dangerous elements in those rocks are dissolved in the water, and they must be disposed of carefully. Wind energy is the most commonly exploited renewable energy throughout the UK. It is often exploited for individual businesses, such as farms, particularly in remote areas. It is common practice to group a number of turbines together in a wind farm. These are commonly placed on windy areas, tops of hills and out at sea. However, even in such windy areas as this, there are days which are quiet and still, and no generation is possible. In order to generate electricity effectively, the turbine has to be adjusted to account for the wind's speed and direction. The rotating blades drive a shaft, and then through a gearbox. The gearbox is necessary so that the generator is always turned at a consistent speed. The generator then produces AC electricity. If the electricity is to be conducted on to the national grid, a step-up transformer will be needed to increase the voltage to a high value. Because there are many wind farms, clearly wind generation must have several advantages. Remote places and single buildings can have their own supply. But for economy of scale, wind generators can also be grouped together in large wind farms. The energy is renewable, it causes no pollution, and the energy resource is of zero cost. Many years ago, construction costs were high, but with mass production and economy of scale, new generating capacity is now very competitive with alternatives. But as with most things in life, there are drawbacks. The supply of wind is not reliable. In particular, the wind is often light on cold winter days. Land-based wind farms are best placed in windy areas, such as the top of hills, but many people find them very unsightly when placed there. Those who live close to turbines often find the noise intrusive, and it is thought that in some circumstances the turning blades can harm birds. The use of hydroelectric energy seems a very attractive proposition. A body of water contains a large amount of kinetic energy, such as in this river. But rivers don't always run full. Rain does not fall every day. So in order to have a reliable source of energy, a reservoir of water is required. There are relatively few hydroelectric power stations in Great Britain, for reasons we'll look at shortly. This one, run by Statkraft in Wales, uses a series of reservoirs, high in the Welsh hills. The dam walls and reservoirs were built shortly after the Second World War, so it is obvious that this is a long-running source of renewable energy. The reservoirs cover a large area and feed water down to generators at a lower level. This model illustrates the process. Water in an upper reservoir is fed through a long tube down the hill, a distance of many kilometers, but vertically a distance of several hundred meters. The water then flows and hits a turbine. Because of the height through which the water has flowed, it hits the turbine at speeds of up to 200 kilometers per hour. These metal turbine blades you can see here are enclosed in the blue housing.
But these are solid guys.
Right.
And that's what's on the arms on every one of those.
Above which are generators. They drive the generators via a shaft which comes through the floor to an upper floor, where the generators sit. To quickly run through that process once more, water held in a reservoir high in the hills runs down through large pipes, several meters in diameter, and at the bottom of the hill, moving very fast and under high pressure, the water plays against turbine blades. Those blades, turning fast, in turn drive a generator. The generator produces AC, electricity, alternating current. That alternating current is then taken to a transformer, where it is stepped up to a high voltage for transmission into the national grid. The generation of electricity with running water has many substantial advantages. It is, of course, totally renewable. It is reliable, it is easy to control, and it has very low running costs once set up. And once set up, it will last for a very long time. In addition, the reservoirs can be used for drinking water as well as hydroelectric power production. The cost of building a large dam wall and flooding a valley, however, is very high, often running to billions of pounds. That flooding is likely to damage surrounding communities and the livelihood of those people who live there. The ecological effect of water flow in, around, and below the dam must be considered. Tidal energy is not widely exploited anywhere in the world. However, the UK, sitting on a continental shelf with large tidal flow all around its coast, seems a rich possible source of energy. By building a barrier across an estuary, the flow of water in and out of that estuary can be exploited in the same way as it is in a hydroelectric dam. As the tide moves out, the water level in the estuary is much higher than that in the sea, and water flows through the turbine, driving a generator. As the tide flows in, the reverse happens. The level in the sea is higher than that in the estuary, and the water flowing in the opposite direction drives the turbine and hence the generator. An alternative system, and rather cheaper, is to place turbines on the seabed where the tidal flow is fast. And there are several of such places around the British coasts. So the advantages of this largely unexploited resource are that it has considerable potential around the UK. It's a total renewable energy resource. Once set up, it's relatively cheap to run and can generate a large amount of energy. A tidal barrage can also be used as a bridge across an estuary and may well help to reduce the risk of flooding. There are, however, several downside problems. The construction of a barrage is extremely costly, running into many billions of pounds. And although the placing of turbines on the seabed is cheaper, it is still an expensive system. There are very few estuaries which are suitable for tidal barrages, and the construction of a barrage may well damage the wildlife on that estuary. And finally, the barrage may impede the flow of silt and possibly sewage out to sea. There are several systems proposed to exploit wave energy. Though none are in large-scale production, most have been tried out. One system uses a large snake of large floating tubes. This line of tubes flexes as the waves move underneath. At the joints between each tube, there is a system of hydraulic rams. These pump oil around the tubes, which then drive a generator. That electricity is then transmitted back to the land. Another system uses a large floating buoy, which slides up and down on a pillar as the waves pass underneath. The movement of this buoy is then also used to pump oil through a system of tubes and again to drive a generator. A shore-based system is potentially cheaper to build, avoids obstruction to shipping, and the costs of transmitting the electricity back to shore. This animated diagram of a shore-based generator shows the waves entering a chamber closed at the top. As the crest of the wave enters the chamber and builds up, the air above it within the chamber is compressed. The compressed air then pushes out through the turbine, driving the generator. As the crest moves on, and then the trough arrives, the volume of space inside the chamber is increased, and so the pressure inside the chamber falls. The higher external air pressure pushes air into the chamber, again driving the turbines and hence the generator. Wave power generation seems to have great potential for the British Isles, with rough seas all around us. It's totally renewable, and the running costs, once established, are fairly low. However, the disadvantages are that construction seems likely to be costly. There is no large-scale production so far. Installations at sea may obstruct shipping, and those on the shore may spoil an otherwise beautiful coastline. All the installations so far have been on a fairly small scale. Domestic solar power generation is pretty commonplace. We see it on many houses, particularly those with south-facing roofs. A few of the panels contain tubes through which water runs to heat up in the sunlight, but the vast majority consist of photovoltaic cells. These cells convert the energy of sunlight directly into electrical energy. They will work in any light, but work best in bright light, particularly sunlight, and therefore best on roofs which face south. The current produced is DC, it's direct current flowing in one direction. An inverter is used to change that DC into AC, alternating current. That can then be used around the house, or it can be sold on to the national grid. The panels use a totally renewable resource. There are zero resource costs. And a major advantage is that they can be used in remote places where there is no other electricity supply, or in single buildings which happen to be exposed to strong sunlight. However, the cost of solar panels, although falling, is still quite high, and the process of manufacture itself uses a large amount of energy, rather spoiling the environmental credentials. And demand for electricity is at its highest on short, dull winter days and at night, when there is little or no output. Thank you for watching.